Hello, everybody, and welcome to this short session on digitizing the physical world. We'll be touching on two topics: opening the black box of digital maps and deconstructing them into their individual building blocks, as well as present you with a couple of geospatial analysis, which will hopefully give you an insight into how they can be used as the most powerful Swiss Army knife when you're trying to gain new insights by using data sets that have a geographical aspect to them. So we'll start out with opening up the black box of digital maps. The image that you see on the screen could be classified as a map, but not as what we call a digital map. And the reason is that this is only a static and dumb image, while a digital map is built from the ground up from individual data sets that represent different types of objects that together make up the map. So when saying that digital maps are built from the ground up from individual data sets, you can think of this, or you can think of digital maps kind of like a layered cake. In this example, we have three different map layers: vegetation, buildings, and streets. And these layers are then all merged down into a single integrated view, which is then presented to the end user. Okay, let's dive into the atomics or anatomics of an object on the map. For example, we've chosen a roundabout. Although being a round circle, this is actually just a line segment. There are enough individual points in the line segment that make up the line to make the line look like a perfect circle to us. And each point in that line is in turn a coordinate set with X and Y coordinates. And the points of the line are read sequentially. As a result, we can determine a direction of the line. And this inherent property of multi-point objects, such as lines and polygons, is typically used in sat-navs in cars and other route guidance applications. There are no wide adopted standards when it comes to attributes linked to geospatial objects. As a result, there is quite a bit of processing job being done when, for example, creating a global map with data from local map authorities in each individual country. In this example, we can see attributes that show which other road segments are linked to this roundabout road segment. And this information can be used in route planning when traversing all linked line segments from the start address to the goal address. In addition, the speed limit attribute could be used to display this information on the map, as well as, for example, warn the user if he or she is driving too fast. And finally, the road segment type attributes, they could be, for example, used in audio feedback to the user. Typically something like, in the roundabout, take the second exit. Very often, the backing data source of a map layer is a database table. Several ordinary relational databases do have spatial support, or they can be extended to have spatial support. As an example, if you're using PostgreSQL as your database, you can add the PostGIS extension to give it powerful spatial support. The tables in your database basically stay the same as before when you add the extension, but you can now add a column with a new geometry data type. And in this example, we've added our first row to the My POI layer table. And POI is, by the way, an acronym for point of interest. The row entry has a category ID column, and we can use the value in this column for choosing which icon we should place on the map. In this example, category ID 3 represents points related to water. And the row entry also has a geometry column. And in this case, the geometry data type chosen for this column is of type point. Other geometry types could be line and polygon, multi-line, multi-polygon, and geometry collection, which in turn could encompass a mix of other geometry types. And we use the value of this column to be able to pinpoint where we should place the icon. to add more objects to our points of interest layer and have them displayed on the map, we would typically just add more rows to our table. Most of you probably know how web pages are put together. You have your structured HTML document that contains what you want to present and a corresponding CSS document that describes how you want it presented. These documents are then fed to a rendering engine, aka a browser, to generate the final output. And by the way, don't worry if you're not able to read the content of the HTML and CSS boxes. The overall point from my side is just that we put some HTML and some CSS into the rendering engine. In the world of geographical information systems, or GIS, the equivalent of CSS is called SLD, Style Layer Descriptor. This is an XML document which can define rendering rules to apply on the points, lines, and polygons that make up the objects in the different map layers. And just the same way as you need a rendering engine to combine HTML and CSS, you also need a rendering engine to combine geometries and SLDs. A very powerful open source example on such a rendering engine is GeoServer. And URLs to resources such as GeoServer will be available at the end of this presentation. Geometry in question is rendered using the applied rendering rules, and the end result can be presented to the user. And in this case, that's a road segment. Diving a bit deeper into the SLD, we can see that it can actually utilize a subset of CSS to define how the object should be rendered. Assembling all the different map layers together, and there could typically be 100 to 200 layers in total that make up a map, that creates the final map that is presented to you, the end user. And just in the layers of the map on this screen, there could be in total hundreds of thousands of objects on these layers, which in turn could be consisting of several millions of individual points with coordinates. And in this example that you're seeing now, we've highlighted just a few of all the map layers and what kind of geometry that they would typically be using, and examples on which attributes that could be used when styling them. And also thinking about the layering, typically the bridges will be put on top of other layers, and houses and buildings will typically be on top of the ground, etc. Okay, let's move on from maps to geospatial analysis. One definition of the term is using attributes in conjunction with the spatial properties in one or more datasets. I would say that it's basically data analytics on steroids, as you have the geospatial aspect as a powerful extra property in the mix. And in these coronavirus times, spatial analysis has been around since way before computers came along. This is a map that was made by Dr. John Snow, who was living and working in London, England in the 1800s. It's showing clusters of cholera cases in the 1854 Broad Street cholera outbreak, where 500 people died in just 10 days. This was one of the first uses of map-based spatial analysis ever to be performed. Each of the black lines on the map indicates a death at that location. And the black lines then stack up to be bars when several deaths occur at a single location, and the same location. Based on the geographical placement of registered deaths, John Snow and his team was able to pinpoint the source of the outbreak to be a water pump at the geographical center of the registered deaths. Note that none of the other water pumps marked in green had any corresponding clusters of deaths around them. Another example, here we have a company that is doing on-site visits at the locations of their customers. The customer dataset could typically be represented as a database table, or if it was a very small company, perhaps just an Excel sheet. But the company has, in addition, also made the dataset geospatial by adding a column of data type geometry. And they have geocoded the addresses of the companies to be able to pin them to the map as points. And since I mentioned geocoding, geocoding is the process of performing fuzzy logic on available address information and finding the closest possible match based on lookups in datasets containing street addresses, postal codes, municipalities, etc., and their corresponding coordinates. So you go from a text description to coordinates for the address. And there is also something called reverse geocoding. That's when you start out with a coordinate set and then perform a least distance analysis towards your address datasets to find the address closest to that point. Our brains are rigged for visual patterns, and this fact can be used to find the needle in the haystack a lot quicker than, for example, sifting through columns and rows in a spreadsheet or a database. Here, the company styled each customer entry based on the assigned seller. And by doing this, they could very quickly determine that a couple of customers should be changed in regards to which seller would be most optimal to assign to the customer to avoid unnecessary travel. And finding this information is, as you can see, done in the split of a second when looking at the information visualized with context styling on a map. But it would be for sure hard or close to impossible to spot if you were looking at the same data in, for example, an Excel sheet. We could build further on our spatial analysis too. For instance, we could add a layer with information about where the individual seller was traveling from, home or office, and then use this to do traveling distance calculations towards each of the customers. We could then do a cost-benefit analysis on the customers furthest away from the seller that they are linked to. In addition to calculated traveling distance, we could also throw some other attributes into the mix. For example, how much revenue we were having on each of these individual customers. Perhaps traveling for half an hour would still be worth it if this was one of the company's largest customers. And our last example on spatial analysis, the ice cream van. We could do an analysis where the desired outcome would be to determine the most optimal locations to stop with our ice cream van in regards to maximizing sales. We could typically use demographic information available with geographic pinpointing to identify the areas with high density of families with children. We could also use distance calculations to the nearest shops and kiosks that could be competitors in selling ice cream, because we wouldn't want our competitors too close to where we're stopping. And this is the kind of geospatial analysis where we could also add a feedback loop. Once we start driving around, we could also register sales linked to each of the locations that we were stopping at. For instance, we could record and store GPS coordinates for each sale. And then we could feed those numbers back into the analysis again to tune stop lengths and visit frequency for each of our locations. That concludes the two topics that I wanted to cover today. Opening up and taking a peek at all the details that make up a digital map, and also how all kinds of different data sets that can have a geospatial aspect to them can be used in geospatial analysis. I know that this lightning talk was just scratching the surface, but I do hope that some of you got some new insights today. Here's a list of some relevant resources that I've put together for you. And with that, I would just like to say thank you for tuning in to this episode of Good Morning with Webstep.